Well, welcome to Lowell Observatory. My name is Kevin Schindler. I'm the historian here at Lowell Observatory, and we're pleased to kind of celebrate a birthday tonight. I'm sitting in the historic 24-inch Clark Refracting Dome because this is the night, July 23rd, exactly 125 years ago, that this telescope was first used by Percival Lowell and some of the other observers here at Lowell Observatory. So we're really pleased to celebrate the Clark this year. Every month we're doing a different program, and then on tonight, on the actual birthday, as it were, we're doing a special program. And I'm pleased to be joined tonight by Dr. Stephen Levine. Stephen is one of our scientists and instrument specialists. He really does everything here at Lowell Observatory. He is an astronomer, but is involved in a lot of the technical aspects of the observatory, making sure the Lowell Discovery Telescope runs properly, and so on. So we're both glad to be here tonight. And we're going to spend the next 45 minutes or so talking about this telescope, as well as our modern counterpart, as it were, which is behind Stephen's head there. That's the Lowell Discovery Telescope. And so what we'd like to do is kind of relive the early days of the telescope, the Clark telescope. First of all, talk about why we have it in the first place, and then some of the reasons why this particular site was chosen, and then when it was first used, and then we'll jump 100 years into the future to the Lowell Discovery Telescope. And what we'll find is that, while we're talking about the history and celebrating this venerated telescope, one of the most storied telescopes in the world, it's not just a historic footnote, it's really what our predecessors did with this telescope, from setting it up to using it and researching. It's the foundation for what we do today. It's not just something that happened in the past, it's kind of a continuum. And that's so much how science is. You build, on they're building blocks essentially. There's the old saying, if we've seen further, it's because we stand on the shoulders of giants. And so what we're able to do with the Lowell Discovery Telescope today, partly that's because of what was done with this telescope years ago. So it's fun to talk about the history, but also put it in context with how it allows us to still do science today, really cutting edge science. So let's talk about this telescope a little bit. We have to go back to 1894. Percival Lowell, wealthy Bostonian, was interested in astronomy. He went to college and studied mathematics. He always had an interest in astronomy, but he didn't go to college for astronomy. But he had spent years in the business world and then traveled for a decade. And in 1893, 1894, he was back in the United States, decided to build an observatory because he wanted to study Mars and prove the existence of life there. And so he wanted to build an observatory of his own. And when you talk to some experts in the field, some friends over in Boston at the Harvard College Observatory, they said, don't do it here. Don't build your observatory here, as in Boston, because if we think back at the time, it's the 1890s, and the Industrial Revolution is still going, and also electric lights are becoming widespread. You have street lights that are shining lights, not only on the streets, but above also to the sky. And so that was blotting out the stars and planets and such. So Percival Lowell decided, okay, if I'm going to build this observatory, I'm going to go where the skies are more pure, not polluted by factory smoke and artificial light. And so he decided to go to Arizona. Arizona Territory, I should point out, because in 1894, Arizona was still 18 years from being a state. So this wasn't even a state yet when Lowell set up shop here. And so, okay, he's going to go to Arizona, but that wasn't good enough. I mean, Arizona's a big state, and he decided on Arizona partly because it wasn't very populated. There wasn't electricity much, if at all, in the state yet. There were no factories here, but also there were several areas that had a higher elevation. And a higher elevation in general means that you can see stuff in space better. It's one of the things we use. Because if you imagine we have air, the air that we breathe, the higher the elevation, the less air you're looking through. Well, that's important because, if you think about a swimming pool, if you ever open your eyes in the bottom of a swimming pool, light is passing through all that water, and that water bends the light and gives you fuzzy images. The same thing happens with air. So the lower the elevation, the more air you're going to have, and the more distortion you get. So the higher elevation you go, the less air, the less distortion. So that's why observatories are typically located at higher elevations. One of several reasons. It also has to do with weather conditions. If the weather was always like it is at this particular moment, and it's pouring rain right now, if you hear a background noise, that's rain coming down on the roof of the Clark Dome. It has to be clear a good percentage of the time, but there's also intrinsic qualities of the air that affect how well you can see. If there's water vapor in the air, you might not see it directly, but it's like if you're driven across the road in the desert, you're looking at the road ahead of you, and you have these mirages of like pools of water. Things like that affect how well you can see through the telescope. If something is blurry with our eye, if we magnify it with a telescope, it's just going to be worse. So they came to Arizona to get away from the pollution, to get where the air is clear, to get to a higher elevation, a lot of different reasons. But once, being out here, they still had to test a lot of different areas. So Percival Lowell hired an assistant, Andrew Douglas, his name was. And Andrew Douglas is just a fabulous character. If you're not familiar with his name, look him up, because after he helped found the observatory here, he later went to found the Stewart Observatory in Tucson, and he also founded the science of dendrochronology, or tree ring dating. So he's a really amazing, prolific scientist of the late 19th and early 20th century. So anyways, 1894, he's a pretty young guy. Percival Lowell sends him out here with a 6-inch diameter telescope and several instruments like thermometers and other instruments for measuring atmospheric conditions in Arizona. So Douglas is going to go from Tombstone to Tucson to Tempe, Prescott, finally up to Flagstaff. And in each place, at nighttime, he'll go out and set up the instruments and take various measurements. So looking through the telescope to see how clear the stars and planets are, but also measuring the humidity, the temperatures, and so on. And so by April of 1894, he was in Flagstaff, and Percival Lowell, in communication via telegram, said, "Flagstaff looks good based on your measurements. Let's choose Flagstaff as the site. It's got overall good weather. It's got good seeing conditions, that intrinsic quality of the air. Higher elevation helps with that. There's no factories here. There's a lumber mill, but that's not very widespread. Aren't electric lights yet. Let's set up shop in Flagstaff, Arizona territory." And so they did that, and they borrowed both an 18 and a 12-inch telescope, and those were set up right where I'm sitting right now, but in a different dome. And they used those instruments for several months, and then they closed the place down, temporarily, because it turns out it snowed a lot in Flagstaff back in those days, and that kind of got in the way of doing their observing. And so what's that have to do with this telescope? Well, after that first year of borrowing telescopes to do some of his early research, Percival Lowell had put it in order with a company in Massachusetts, the Alvin Clark and Sons telescope making firm. He ordered a new telescope, the best of its kind, the best that money could buy, because that Percival Lowell could afford it. And he ordered this 24-inch refracting telescope that measures 32 feet long, and it was ready in 1896. And in the meantime, they had Andrew Douglas and Percival Lowell had come out here. They had a lot of weather issues, And so they did some more site testing, and they went to different areas, and they ended up deciding, let's set this telescope up in Mexico in 1896, because there's another good opposition or close approach of Mars, and it's going to look really good in the sky, but it's going to be better if you go a little more south, where it's going to be higher in the sky. So they did some more site testing, decided to put this telescope down in Mexico. So they brought it, they tested some, used it down in Mexico, but at the end of that season, they decided, this was good for this season, but let's take it back to Mexico because it's a lot more convenient there. And maybe we'll stay in Flagstaff after all. Sometimes they have bad weather, but then you have long periods of good seeing. So they brought it back here. But when they first got the telescope, it was first of all ordered in 1895. In the spring of 1896, the tube was finished. And so that was shipped out here to Arizona, put on a wagon at the train station, brought up the hill, and the tube was assembled. And I make this sound so easy, but it wasn't. I mean, these are pieces that weigh thousands of pounds. We didn't have cranes to lift this into place. It was all done by using ropes and pulleys and systems similar to that. So the assembly came out in the spring, and by July, the lens was ready. Percival Lowell brought the lens out himself in a crate. It was the two lenses, but the important parts, there's two lenses in the telescope that do the work. They measure 24 inches in diameter, and together in the cell that held them is about 150 pounds. So Percival Lowell had them packed in camel hair, brought them personally on the train, arrived in July, and July 22nd, so the next night, July 23rd, they had put the lenses in the telescope. In July 23rd, 1896, used this telescope for the first time. And they looked at Mars and some other objects. And then they did some more testing. That was on site right here. Then they took it down to Mexico, used it down there, then brought it back. And it's been essentially here ever since. So the early days of the Clark, there's some neat history of the site testing that went on, the very reason for having a telescope in the first place. And then building the telescope, and then ultimately the first light. When you first, in this case, look through an eyepiece. In the case of modern telescopes, you're not looking through an eyepiece, but Stephen will explain more of the technique. But when you first use it, that's the night called first light. And it's a magical moment, one that you've been holding your breath for years. And when you get that first look, and it comes out as good as or better than you expected, that's a great moment of celebration. And that's why 125 years ago, or 125 years later, we're celebrating again, because it's such a magnificent accomplishment. And the history of this telescope, all the research that's been done with it, the first evidence of the expanding universe, Percival Lowell's observations linked to his ideas about life on Mars, the astronaut training here, moon mapping in support of the Apollo program, and the millions of people today through our education program that look through this and get inspired about the cosmos, just like Percival Lowell did. It's got quite a storied history, and certainly worth celebrating. So I just wanted to recap that history of the telescope a little bit, because this is the night they first used it. But then also, again, tie in, why do we care today? Okay, that was something neat that happened years ago, but that's more than a century ago. Why do we care today? Well, one of the reasons is because, as I said, this laid the foundation for what we do today. Doing site surveys today is a lot more complicated than it used to be. And building a telescope, and the telescope itself is a lot more complex than it used to be. But it's based on what we did back then. We keep building and building on the technology. So what we'd like to do now is to jump to the present. And when I say the present, I mean we'll say the last 15, 20 years or so. And remember how the Clark telescope came about and the site testing we did and such. But now we're gonna look at how we did that process with the Lowell Discovery Telescope. And the Lowell Discovery Telescope, while this Clark telescope was one of the finest telescopes in the world when it was built in 1896, the Lowell Discovery Telescope is one of the finest telescopes in the world today, and one of the most adaptable and diverse telescopes in the world. So, Stephen, let's talk a little bit about the Lowell Discovery Telescope. Thanks for joining us. And first of all, you know, for the Clark telescope, one of the main things that Percival Lowell was trying to accomplish was to study Mars, but he certainly studied other things. He studied planetary bodies. V.M. Sliper used this for the expanding universe studies and such. So if it's such a great telescope, why did we need to build another one 100 years later?
Well, and thank you, Kevin, first of all. And that was really quite, I always learn something when I hear your discussions about the past history of our equipment. And before I directly answer, it's interesting to note that essentially telescopes, cutting edge research telescopes, are essentially built for the long term. And you know, here we are 125 years later, and the Clark is still used. It may not be primarily used for research, but it's still a fully functional, usable, and used telescope. And that kind of thinking informs the building of every major modern telescope, the Lowell Discovery Telescope as well. And so just as when Lowell was figuring out what he needed to do his science, he was originally interested in Mars, but as you so well pointed out, there were a number of other programs that were directly doable with the instrument. We did a very similar sort of thing starting back in actually the 1990s, trying to understand what are the current Lowell scientific interests, what kind of programs are there, but a 24-inch doesn't quite have the aperture to be able to see things as faint as a larger telescope. And as time has progressed, the edge of the envelope where people keep looking goes fainter and fainter. And partly what fainter means is, for solar system bodies, it often means smaller and often more populous. But also for people studying large-scale structure in the universe, it means fainter galaxies further away. And some of these things are simply too faint to reach with the 24-inch. And at the time that the observatory was considering a new instrument, the observatory already owned several telescopes that were larger than the Clark by this point. But like I say, where modern observational science was kind of keeps progressing to larger and larger collecting area at the same time that the instrumentation to go with it has progressed. And so when the observatory started thinking about, we need a new instrument to put us, to give us direct access to, well, to help our observing programs be scientifically germane and competitive. It wasn't specifically well, we set out to build a 4-meter telescope. It was more, we set out to build an instrument that would be appropriate for the kinds of research we're trying to do today. And it is fair to point out that large research telescopes, and this has always been true at some level, are fewer than you would like, and time is always precious. And so the fact that the observatory actually owns its own 4-meter class telescope puts us in an unusual and very positive position to be able to consider programs that you might not be able to consider on an equivalent telescope owned by someone else. Mm-hmm. So there's a lot of pieces that factor into it.
Yeah, okay. Now, I'll point out that we're kind of operating live from Lowell Observatory campus here, but we're glad to have people joining us, everybody joining us, and this is open discussion. So if you have any questions or comments, or if you've used these telescopes in the past and want to recall something about that, just send a note in via our YouTube comment section, and our staff will share it with us, and we'll answer those when they come in. So Stephen, so we know why we want to build a telescope. We've decided as an observatory we're going to build what we know today as the Lowell Discovery Telescope. So what were the steps taken to find a spot for it? Just like Andrew Douglas was sent to do site testing around the territory. And I'll point out that took place over the course of about 5 or 6 weeks. That was the entire site testing across the territory of Arizona. Let's compare that to what was done with the LDT.
So, in fact, the process of sighting a telescope is intimately related to the science you want to do with it. And even before you start testing a site, you have to think of a couple of things. One is, where are the objects that you're interested in the sky? And so, if your scientific interests are driven predominantly by, let me choose not exactly randomly, the Large and Small Magellanic Cloud, then sighting a telescope up here doesn't do you any good because you can never see them. And so it sounds simple, but you have to decide roughly where on the globe you want to be in the first place, even before you worry about the local topography. Once you've made that kind of a decision, and for Lowell Observatory, many factors come into the decision. One of them being simple practicality. Lowell is located, as you noted, in northern Arizona. If we wanted a telescope in, say, the high desert in Chile, which is where a lot of the more recently built modern telescopes are, support for such a facility is a much bigger and much more expensive proposition, usually done by large consortia. So part of the thought went into that, but part of it was as well, most of the development had been in the South in the last 40 years. And there was a thought, well, there's real advantage to Lowell if the telescope is directly accessible. The Discovery Telescope is only 45 to 50 minutes outside of town. And so from a practical perspective, we can go out and fix something in real time, or we can test something in real time. But once you've made that choice, so in this case, it was Northern Hemisphere, Southern Hemisphere, our decision was essentially somewhere that we could get to relatively easily. So say within an hour and a half to 2 hours drive from town. Then the process is actually very much like what Andrew Douglas did 125 years ago. And the truth is, if you look at the whole process, virtually every step he followed has a modern analog. The difference being we probably spend more time on it, and there's probably a whole lot more technology involved than there used to be. And so the first step in site testing was to look at the local area and say, well, what's within 3 hours of Flagstaff? And then who owns it? How tall is it? And from that, you sort of winnow it down to several dozen possible, typically hilltops or mountaintops. And then you do sort of a quick survey of what the weather conditions are. The Weather Bureau is your great friend, because you want to know, well, in the long term, over decades, is this site predominantly clear? What's the rainfall like? As you pointed out, is the water vapor column problematic? Because if you want to work in the near or mid-infrared, that is a very, very important driver as to whether or not you can do this. And then, so you use that to winnow it down again. And then finally, you get sort of feet on the ground with telescopes in hand. And we would take out a system that Douglas, at some level, would recognize all the parts of. It would be a slightly larger telescope with an electronic camera, but basically we would be going to a site, setting up, and looking at the image quality, the quality of the stars that you could see from the site, night after night, and assessing that and recording it, and looking to see, is this site delivering consistently good, i.e. very sharp images of the stars, or are they typically sort of fuzzier, or is it often more cloudy than you thought? And so the process, for us, the site testing process really kind of kicked off right around 2000, 2001, and was wrapped up by about 2004 with the selection of the site at Happy Jack, where the Discovery Telescope is now. But the last step of that was the better part of a year and a half worth of testing just that one site. So, like I say, Douglas would recognize it, but we spent a lot more time on it.
So we've found a good site for this. for the telescope. What about the construction? What kind of time frame was that? And was that a pretty straightforward experience for the Clark? It was pretty removed from the observatory staff. That was something that Percival Lowell went to pick out the lenses for this telescope, and that's a big difference. This is a refractor with lenses. LDT is a reflector with mirrors. And so he went out to pick out the lenses, but then pretty much it was in the hands of Alvin Clark and Sons to build it and bring it out here, and then our staff could try it out. How was that similar or different from the process with LDT?
There, again, would be some similarities in the sense that large telescopes are contracted out predominantly, just in the sense that if you look at least the image behind me and you can see the small person over my shoulder, to give a sense of scale, you need shops capable of an enormous range of abilities and capabilities. So you need mechanical shops capable of building something that, and the telescope itself is 135 tons worth of metal, but that has to move with micron precision. And so you need mechanically facile corporations, but you also need someone to design and fashion the optics. Totally different requirements in terms of capabilities. In our case, it wasn't simply calling up your prime contractor. For Lowell, it would have been Alvin Clark and Sons. For our case, it would have been basically General Dynamics Satcom as the prime contractor. But we actually had, in the process of moving to construction, Lowell, the observatory, assembled a team in-house that would be responsible for overseeing the entire project. And they were very much, this is between 4 and a dozen people, depending upon the time of the project, who represented a whole range of talents, because you have to have that information in-house to be able to assess what your contractors are doing. Is it meeting the specifications you have? And so we actually had a Discovery Telescope office that was led by the project manager and a project engineer who would, some of it was bookkeeping in the sense of making sure you're on budget, but some of it was also very much making sure that the vendors were coming back and saying, yes, this component will meet your specifications. And making sure that everybody's timeline meshed, because you don't want to find yourself with, say, the optics done 3 years before your mount is ready for them, and then the optics have to sit somewhere. And so it's very much a joint venture at that point between a significant number of people on the observatory payroll and the vendors we're working with. For us, in this case, the optics were a joint venture in the sense that Corning Glassworks in upstate New York actually provided the glass for the mirror. So, if you followed the mirror, the timeline of the primary mirror on the telescope, which is 170 inches in diameter, that glass was selected and slump cast into its rough shape at Corning. And then it was trucked across the country to be ground and polished by the College of Optical Sciences at the University of Arizona down in Tucson. And it took several years for all of those steps. And then the last step, of course, is that they finish polishing and then they deliver it to us. Meaning, of course, that you truck it up from Tucson to Happy Jack. And at every major step along the way, group members of the Discovery Telescope team would have been involved in reviewing the status. When Corning delivered the blank to the College of Optical Sciences, we had representatives there to oversee and to look at what Corning said the status of the glass was, what they knew about the pluses and minuses of it, and to talk to the folks at the Colleges of Optical Sciences to make sure that they were comfortable with what they were receiving. So it really has become very much an integrated kind of a process. It's not just call up your local telescope vendor and say, I want a 4-meter, please have it for me in 2 years. Because truthfully, in this case, it's closer to a decade-long process. And if you look back at the telescope timeline, there are the external vendors building the telescope, essentially at their facilities. But at the same time, we had construction companies like M3 and BEC actually working to clear the site where the telescope is at, to pour the foundations, to build the external portions of the dome itself, all before the telescope showed up. So that when it was finally ready, I mean, by the time they brought the telescope up in pieces, they literally hoisted the pieces through the slit of the existing dome. But to give you a sense of how long this kind of thing took, it wasn't weeks. You know, they broke ground at the site in 2005, I think. And we didn't actually have a telescope to try out on sky till the latter part of, well, 2011 roughly. Mm-hmm. So it is a big and a long-term project.
So it was several years, a lot more complicated than 100 years ago. Let's talk about that first light. What was that like for up here at Lowell Observatory? It was, you know, when they first used the Clark, I mean, this was a big day for Percival Lowell and his staff, but it wasn't something that the media was there for, or I don't think they drank champagne or anything like that. It was just, okay, the telescope's here, let's get going on observations. What was it like first light for the LDT?
Well, I mean, in a sense, for us, first light was sort of many first lights, because we had pieces of the telescope ready enough to test, and it's a complex enough engineering project that, in fact, what you want to do is try to test each piece individually if you can. So, for example, in late 2010, we didn't have the optics, but we had the mount. And so one of the things we could do is we could say, well, we don't have a mirror, so it's not a complete telescope. But we also have no idea how well the mount actually works. I mean, the mount was built in a factory and tested to move to the best they could test, but that's not the same as pointing at a star and going, there it is. And so what we did was we actually bolted a small finder scope onto the side of this massive mount. I mean, for any of the amateur astronomers in the audience, we bought a standard 80 millimeter finder scope. So, you know, the lens on this is about this big, the thing is only about this long, bolted to a 135 ton mount. Mm-hmm. And for the first few weeks, we had the smallest telescope on the biggest mount, just so we could test out how well the mount worked. Could we point it? Could we find the moon? I mean, it sounds absurd to say we just built this enormous high-tech telescope, but you're not even sure you can find the moon, which any school child can point to. Mm-hmm. And so the very first light for us, in a sense, was, look, we can finally point the mount at the moon and get an image of that in an 80 millimeter finder. Now, no one is going to call that our first light, but it is indicative of each of the steps we took along the way. And so when we finally put the primary mirror in, we didn't have a secondary mirror yet, which would be the mirror up at the top end. So what we did was we had the primary down here to reflect the light. We put a camera up here instead. And then we were able to get direct images using our primary mirror and to test out all of the support structure for that mirror. And in a sense, we got a first light with that too. And then 3 or 4 months later, the secondary mirror was done and we put that in, and we were able to get light down at the bottom at the focus we use for most of our instrumentation now, but the camera wasn't ready yet. And so much like Douglas and Lowell would have done, we actually did put an eyepiece on the back of this thing. But perhaps even more crudely, even before we could mount an eyepiece, with the telescope pointing well enough that we could find, in this case, Jupiter, several of the other members of the staff and I were out there one night, and the question came up, does the telescope actually have a focus far enough back that we're going to be able to get light into the camera we're building? And so what we did was we went up to the back end of the telescope, which is just an open hole at this point. And I took a piece of lined paper. We pointed the telescope at Jupiter, and you could look up through the hole and go, well, there's Jupiter. And we literally moved the piece of paper back and forth until you projected an image in focus of Jupiter on the paper. And thankfully, that piece of paper was far enough back from the back plate of the telescope that we knew it would focus in the camera. But Jupiter's fairly bright. The thing that really got me when I thought about it for a minute was that not only could I see Jupiter through the piece of paper, and I could see the bands on it and the great red spot, I could see the 4 Galilean satellites projected through the paper. We were collecting that much light. And so in a sense, that's another first light for us, a technical first light. And then finally, in the spring of 2012, we had a camera to put on, and we would have what people would refer to as the official first light, where we had all the components in place acting together. And we did actually pop a cork of champagne upon receipt of the first image. But there must have been 8 or 9 people in the control room at the time. And it's a very visceral experience to see, even having done each of the steps ahead of that, to see it all come together at one time to give you that image. And I think our first image was, in fact, one of the Messier galaxies, standing there in clear, sharp focus on our electronic cameras.
And I'll point out that, for the Clark telescope, first light on July 23rd, 1896, was a culmination of about a year project that cost $20,000. In the case of the Lowell Discovery Telescope, it was a project that took, 8 years, or at least something like 7 or 8 years, and it was a $53 million project. So different scales there in a lot of different ways.
I mean, it depends almost on where you want to, do you go back to the germination of the idea in the 1990s?
Yeah.
Do you start from when they turned the first shovel of dirt in sort of the mid 2000s? I mean, even from groundbreaking to the time when we finally declared it fully operational was a decade. And in a sense for us, First Light was another beginning, because we had a whole bunch of commissioning work, which was really taking it from a full up construction project to a fully functional science instrument. And we did First Light in 2012, but we released it for full operations at the very beginning of 2015, which was not to say we weren't doing science before that. So it's very much a continuous process.
And it's interesting, as we're talking here with Dr. Stephen Levine about the parallels and how history repeats itself some ways, or at least sets the stage for what's to come. This historic Clark telescope that we're celebrating tonight 125 years ago really helped set the stage for the Lowell Discovery Telescope and the continuation of remarkable research by our astronomers. So we've got, time flies, but we have a few minutes for questions. I was kind of holding off on those so we could kind of get through the story there, Stephen. So let's go through a couple of questions. Here's one: was observing on winter nights a chilly business in that era of first light? Well, I might start that answer, then maybe you can finish it, but I'll start by saying Flagstaff can get chilly at night, depending on the time of year. And it's one thing that hasn't changed. If you're at the telescope domes aren't heated. So the telescope itself is going to be hopefully as close to the temperature outside as you can get, so that the temperature of the air inside is the same as is outside. Because otherwise the telescope's going to be looking through the interface of warm air hitting cold air. It's like two weather fronts. You're going to get all this bad seeing. Now, one thing that we have today are warm rooms, and that certainly helps. So Stephen, I'll let you take over from there and what it's like to be out there.
And it's certainly the case that the Discovery Telescope was designed with the assumption that observing would be done essentially from what seems like a very mundane control room sitting in front of a computer screen. It's much less romantic than the thought of standing out under the stars. On the other hand, January outside of Flagstaff, it is easily sub-freezing. And we actually, for most of the research work, it's handled from the control room. But we have on occasion put an eyepiece on the telescope, at which point we all troop up very dutifully to the dome and freeze as long as necessary, because the truth of the matter is there's nothing like looking at the sky through a 4-meter class telescope. We started this during the process of commissioning, partly because it helped us figure things out, but partly because it was fun. And the truth is, among the very first things we looked at by eye outside of the planets would have been the Great Nebula in Orion. And it's one of the few cases I can think of where you can see, with a 4-meter telescope, you can see color by eye, but you're also standing there in January freezing. And so, you know, we ended up spending 2 or 3 hours one night doing this before someone said, you know, we really need to get back to work. So yeah, it still happens, but most modern observing is done from a control room.
Now, on the other hand,
people, yeah.
If you come to visit, if you're a visitor that wants to come and look through telescopes yourself, the observatory's public program, we have a stable of outstanding educators who, during regular times, will have telescopes open every night and tours regularly. Right now, we're still in COVID protocol, so we're still reservation only, group sizes of 10 or fewer. We hope to be moving past that in the ensuing weeks, but that's where we are right now. So it's really neat to be able to come up here and look through telescopes, but you know, the winter time is when we tend to sell the most sweatshirts in the gift shop, because you can be standing outside looking through a bunch of telescopes, and it can get quite chilly. And you know, you talk about the romance of standing outside under the stars. It's quite romantic, and it also can be quite cold. So it's kind of a mix. Now we have just a couple minutes left. Let me get to these. We have a hello from my space cousin, Joe Schindler in Chicago. Joe was one of those outstanding educators for several years here. And the question is, the observatory open for tours? I just mentioned that we're in COVID protocol. You can get online and make reservations. It's reservation only. And then soon, relatively soon, we can't put a time on it yet, but once we open up back to regular operation, then we'll be able to welcome a lot more visitors again. And so let me get to this question from Pablo. Are the telescopes being used for modern research? I'm searching for NEOs, exoplanets, etc. I'll start by talking about this one. The Clark is not used for modern research. I mean, technically it could be. It could have been outfitted with modern equipment and stuff, but this telescope is so important historically and educationally. We have, in non-COVID years, we're getting 100,000 visitors plus coming through here, and those numbers are going up. And so the number of people that can look through this and be inspired by the cosmos is, you know, that's one of the reasons we're here. And so we could use this telescope for research, but its value to inspire and to be used for education is really, you couldn't match that. As for the Lowell Discovery Telescope, Stephen, I'll let you talk about that a little bit.
Yeah, I mean, not surprisingly, it was built to be one of our primary research instruments, and it is used at least 300 nights a year for research, weather permitting. We actually do, there is a whole range of solar system related research. There are folks doing searches for near Earth objects and follow-up studies of them. We have a number of folks who are regularly observing exoplanet transits. We also have folks doing various forms of stellar research, both imaging and spectroscopy. We have folks with interests in larger scale structure, people who are looking for faint structures in external galaxies. So, I mean, the telescope is designed to facilitate quite a wide range of stuff, and the instrumentation on it includes both imagers. The imagers we have are typically CCD detectors, and we have those, and the detectors in our spectrographs tend to be electronic detectors, CCDs or CMOS as well. So it's all electronic pretty much, but one of the neat things about the telescope is that we are capable of carrying and do carry 4 or 5 instruments at a time. And one of the really unusual aspects is that a researcher can make use of several instruments practically simultaneously. And that means that, if you're looking at something and you're getting spectra, you can get images as well, or vice versa. Or if something unusual crops up, you can switch with 5 minutes notice.
And that flexibility is one of the reasons why our former director nicknamed the LDT the Swiss Army knife of telescopes, because it can do so many things and do them efficiently and quickly. Well, Stephen, it looks like we're about done on time here. So thanks so much for joining us tonight. It's been fun to relive 125 years of this telescope and its modern counterpart. Thanks for joining us tonight. And thank you, Danielle and Heather and Maddie, our behind the scenes crew, for making everything work well. And thanks everybody for joining us tonight. We'll see you next month as we continue celebrating this historic Clark Refractor and all we do here at Lowell Observatory. Good night.
Good night.